Let's see. Okay. Now we're going to talk about something very interesting. Okay. Now we're going to talk about your actual body's energy. So usually when we say body, we don't, like I said the first day, we don't mean your body. We mean like a mass or a boring block or something like that. Now I mean your actual body. Oh, that brings up the questions. I have questions about my body. Does velocity have to be constant to use the F-W equation? No, there's a more general equation when the velocity and the force change. But we don't want to get into that. We're just going to do constant velocity things. We're going to keep it simple. Or not simple, but doable. Okay. Yeah. Okay, so your actual body. Okay, so when we thought about, okay, we raised the block up to some high level and we had energy stored because suddenly we can make it release some energy, right? So I can just stand here and I can start moving around, right? So clearly there's some potential energy. There's a lot of potential energy here, okay? A lot, okay? So you have stored potential energy. Maybe I'm made up of small springs and mechanical devices on the inside. Sometimes I wonder. But it's actually in chemical bonds in the crap you eat. The garbage that we eat, somehow your body can still turn into useful things. It's amazing. Just go to the commons and look around. You'll be in awe, okay? C6H2O6, right? Glucose. You could just sit around and eat glucose and see how long that lasts. But what your body does, takes C2H6, whatever the hell it is, glucose, plus oxygen. I know what that is, right? Carries. Oh, is this bad? I'm going to draw DNA later. Oh, did I screw this up? C2. Oh, I'm missing one. Oh, sorry. Oh, my God. So there were 2 mistakes in last year's lecture. Okay, good. So your body burns this, right? You breathe in air. It has oxygen in it. Burns this. Gives you, let's all do it together, 6CO2 plus 6H2O plus energy, which is like ATP, right? The physics part is that releases energy, and you don't just want it where the oxygen's burned. It makes it into ATP, powerhouse of the cell, some bullshit like that. I don't know, okay? And then your cells use the ATP to make things happen, okay? So if we want to do a quick calculation of how this could actually apply, right? So let's imagine we run up the stairs here, right? So you're here. How we would do a physics calculation. And then you run up the stairs, and oh my God, you're tired, right? Okay, right. Run up the stairs. So let's think about what the energy transformation will look like if we wrote it as like in the delta kind of formulas. We'd say the change in energy, and now let's look at all the terms we've learned about. The change in kinetic energy, plus the change in gravitational potential energy, maybe that's a number, plus the change in spring or elastic potential energy. Certain kind of Nike shoes might have a term there if you compressed and didn't lift up, but probably not. Plus the change in thermal energy, right? Plus the change in chemical energy. That's your glucose. You can have all kinds of potentials other than just sort of gravitational and spring. So all I want to do now is run through this process and say, are they 0, positive, or negative? And then you would be able to solve the problem, right? If I asked you, how many joules do you burn going up here, you could probably figure it out, except for the heat part, right? So let's see. We know that if this is an isolated system, let's imagine we're not thinking about anything else, that this is 0, right? What's the change in kinetic energy? 0. But here we go. What's the change in kinetic energy? 0. And that's my 0 face. There you go. What's the change in kinetic energy? It's 0 because he started from rest, and clearly he's ended at rest, right? Because he's tired. What's the change in gravitational potential energy? Positive. Right, he went upstairs, right? So positive, it would be mgh if this were an actual problem. What's the change in elastic potential energy? But he aged while he went upstairs, and the springiness of the collagen in his joints changed. No, let's not do that. Okay. It's 0. You don't know about that yet. And then what is the change in thermal energy? So you talked a little about Tuesday. Is he going to heat up or cool down? He's going to heat up. So this we would have to give you. In a problem, we would just have to tell you probably that he generated a certain amount of heat. Or maybe in the problem, you would have to solve for how much heat did he make. right? Because that's like there's no formula for that usually for something as complicated as a body. So therefore, what must be the change in the chemical energy? It's positive, positive, must be negative, right? So the idea here is the energy exists in your body. You have a positive high potential energy due to glucose or other chemicals in your body, and when you move around, you burn them. And the change in your potential energy is negative. It doesn't go to zero, hopefully. It's just negative. Okay. All right. So I think the homework has one problem like that, where you work out just some simple numbers. Okay? And these aren't big, complicated physics problems. These are just to get you thinking about this a little bit in the real world, not just masses and springs and friction and all that. That's all the physiology we're going to do today. Oh, wait, no, it isn't. Hold on. What does the word on the left of the stairs say? Hold on. I'll be right back. Oh, you mean on the drawing. No, sorry. That says potential energy chemical. That says ATP. I'm not going to try it. And that's negative. Amino triphosphatase potato. Okay. What if the velocity was a diagonal vector and the force was a horizontal vector? Would it still be found using cosine 45? Yes. Because as we talked about last Thursday, dot product commutes. So it doesn't matter which vector you think of first. It's just the angle between them. Make it positive or negative, your calculator will give you the same answer. Okay?